So, I don't feel bad about it at all. Okay, thanks for interrupting and making me a behavior specialist, which I don't get paid enough to do. All right. This is DNA replication. So first thing you're going to say, gentlemen, is what are the 3 parts to nucleotides? Phosphate is one of them, the deoxyribose, which is a type of sugar, and then the nitrogenous, and nitrogen bases, which are adenine, thymine, and cytosine. Okay? Why does adenine go with thymine? Remember, it's got 2 hydrogen bonds that form, and then cytosine goes with guanine because it will form 2 hydrogen bonds, or 3 hydrogen bonds, excuse me, okay? Which we went over last week. That's why those 2 go together. So you're gonna get this. This is what you're gonna get. Nucleotides, like this. And by tomorrow at this time, there'll be so many cut out that you probably won't have to cut out anything. Does everybody follow that? So you're gonna have these. You're gonna have the whiteboards in the back. They're gonna be nicer colors and probably thicker. And then you're gonna have some loose nucleotides. You'll see why here in a minute. So you can build 2 strands. I should have 2 DNA when I'm done of this, a copy of this, okay? So that's the process we're gonna talk through. How do we know it's DNA? DNA double strand, and it's got thymine in it. It's got a T, always. Okay, pretty simple. So you'll have markers, you'll have erasers. Some of you might want to actually make some of the components. Okay, so the components that you're going to need tomorrow: hexacase, DNA polymerase, lagase. I've already written 3 to 5 on this. Remember, we read 3 to 5 and we build 5 to 3. We're going to go the opposite direction on this other one. I'm going to label the leading strand and the lagging strand, so I have to talk about that, and I have to talk about Okazaki fragments. Okay? I already talked about nucleotides. Replication fork needs to be there. Okay? So, boom. Here we go. Might be recorded again, yes. All right. So, first thing, DNA hexacase unzips DNA. This is in the S phase of interphase, where we need to copy DNA to split it into 2 cells. So we're going to, hexacase is going to unzip DNA, okay? And so we now, because we started right here, this is my replication fork, okay? And there's a reason why I got that there. I'll show you that in a minute. But then there's this little enzyme that comes in and puts a primer on there. It's called RNA polymerase. And so it puts on a little primer. So our DNA polymerase can hook up, okay? So DNA polymerase is hooked up. And so DNA polymerase is going to do exactly what you would do. If I said T, what am I going to put with it? An A. If I put, say, G,
C.
C, if I have a T, so it's doing that. It's bringing in nucleotides based on what's there. And it's moving that way, and it's just going to keep going until it runs out of DNA. So this is my leading strand. Good. My leading strand. It's just going, copying DNA that way. Okay? Notice that I used this original strand as a template. Okay? Meanwhile, another RNA polymerase is going to put a little primer right here. Primer is like to say, hey, dummy, start here. That's what a primer does. A little RNA primer, start here. And then another DNA polymerase is going to hook up, and it's going to do this. What do if I have a C, I need a what? G. So you'll notice right now that I'm having to look, which is not what you want to do tomorrow, because you don't have time. Okay? You don't have time to mess around and do anything. If I see an A, I'm going to put a what?
T.
T, so I need a thymine. And then these guys are hooking themselves together, covalently bonded. And then if I have a C, I'm going to put a G. You get where this is headed? Which way am I moving? I'm moving that way, right? And if I keep going with this, what's going to happen eventually? I'm going to run out of DNA and I'm going to run into the replication fork, yes? And because of that, I have to leapfrog. And because I leapfrogged, I now have another primer that was put here, and guess which way I'm going to go? Back towards the replication fork again. So I'm going to work this way again. And as I'm working this way, hey NASA, what are you looking at, dude? Yeah, you're not really paying attention, you're hanging out on your phone. Am I wrong? That's weird. How can I tell that? Yeah, because you're swiping. These guys aren't swiping. And I have one eye, I can see that, so imagine what else I know. Got it? You realize you acted like this first day of school here, right? Look at you now. Okay, so we're moving this way, lagging strand, right? And then we're getting to the part where we're running into this again, yes? And so because of that, we got to go the heliexicase open that way more, and it's got to jump way, it would be over there. It leapfrog back. And notice I have a gap here. Yes, I had a gap here. Now I have another gap here. Those are your Okazaki fragments. Okay? So I have DNA over here, but it's got a little gap in it. And so a scientist discovered that these little fragments in DNA are happening, so they figured out this is called the lagging strand, which you have to label. The lagging strand, because the Okazaki fragments happen because that DNA polymerase is having to leapfrog back and forth. So there's a gap in the DNA. The last thing you need to say is this, because that guy's moving too, right? The last thing you need to say is that lagase will come along and connect the Okazaki fragments. Okay? So I got lagase. And then when you're done, you should have, hypothetically, 2 DNA going in the opposite directions, correct? Hypothetically. This one needs to be switched, but that's okay. Questions? You have to have questions. So when you're done, it should look like that. Okay. So I labeled the leading, I labeled the lagging, I have a replication fork. I discussed that lagase goes and connects those Okazaki fragments. It would be good to show it on the whiteboard because you could have more room than I have here, right? That there's going to be fragments. And then the last thing you do is fill in that last fragment, and you should have 2 identical strands. So I have a T here, yep, T, A, G, G, right? I have the same DNA, duplicate of it, okay? So, in this video, you have those things. You have 1 minute to do it. 1 minute, it is possible. 1 minute, I think this was one of the first ones that ever got embedded. Second one, because we did mitosis first. You have 1 minute. You have to have 10 or more nucleotides, which is going to be easier to have more than that anyway, and you'll have access to a bunch. You're going to need to label leading, lagging, 3 to 5, 5 to 3. Label Okazaki fragments, polymerase, lagase, heliexicase, right? That was at the beginning. Nucleotide, I think that's all it says behind me. Oh yeah, last thing. Original strand, right here, yes? These are all new on the inside. Original on the outside and new on the inside. So it's complementary. So, questions? I'm taking any questions right now because I want you to be ready. Go.
Why is the timing from
Yeah, so if we go back and look at the structure, I'm going to give you a very crude picture, okay? So if I have adenine, right, adenine, thymine, on the end of one of them, I can't remember which one, there's a hydrogen, and there's the opposite on it. And those hydrogens are positive charge. And then there's like an oxygen there and a nitrogen there, and those are slightly negative charge. So they create this hydrogen bond. Why? Yeah, we'll stop class and talk to you about that you need to go to the office. Go to the office, yeah. Take all your stuff, would you? I don't know what to do anymore. Did that help? This is what I wanted to do when I signed up for this teaching gig. So on cytosine and guanine, the opposite's true. So they would repel each other, is why they don't hook up, and there's 3 hydrogen bonds there. Other questions? Yes?
What exactly does lagase do again?
Lagase, so if we have a, so it might be good to just do this. So I got this DNA going, right? This is my lagging strand, and so I had to leapfrog back here, and I'm all building DNA, right? So I have Okazaki fragments now. That's one fragment. There's another fragment. And so lagase will come in here and actually connect those two because the polymerase can't get away. It won't be able to pull off if it connected it. So because it can't, it leaves a blank spot. And because it leaves a blank spot, lagase comes in there and fills it in.
We go over
Okazaki fragments. So on the lagging strand, again, right? Remember I leapfrogged here because I ran into the replication fork? So I jump back here, right? And so I get here, well, I've still got to go your direction generally, but I got to leapfrog back. And so as I leapfrog back and I start closing these off, it leaves these little sides right here, right? Those are the Okazaki fragments on the lagging strand. The lean strand doesn't have them because it just goes. Other questions? Yes.
Is the R enabled? Which one creates
primer?
Yeah.
So let's say, go back to our Okazaki. So there's a primer that comes in here that basically just says, hey, dummy, in red, start here. That's it. RNA primase just puts a little primer on that says, hey, start signal. Just attach right here and go. Okay? Anything else?